Welcome to a lesson on the area of a parameterized surface, and we'll also introduce the idea of a surface integral. So if we want to determine the area of a surface as we see here in gray, the idea starts by picking a point on the surface defined by r of uv and determining two tangent vectors, one in the direction of the v-axis and one in the direction of the u-axis. So this vector here would be delta v times the partial derivative of r with respect to v, and this vector here would be delta u times the partial derivative of r with respect to u. So we have the change in v times the change in r with respect to v for this vector here, and here we have the change in u times the change in r with respect to u for this vector here. And now to determine the area of this tangent plane, we can determine the magnitude of the cross product of those two vectors. So our area would be equal to the magnitude of delta u times the partial derivative of r with respect to u crossed with delta v times the partial derivative of r with respect to v. And we can rewrite this as the magnitude of the cross product of the partial derivatives times delta u delta v. So this would represent the area of one small tangent plane. So we know by now that if we want to determine the surface area of this entire surface, we want to determine the area of more and more of these very small tangent planes, which involves a limit as n approaches infinity of the sum of the area of these tangent planes, which gives us the double integral to determine the area of a parameterized surface. It's going to be equal to the double integral over the surface integrated with respect to s, which is going to be equal to the double integral over the region in the UV plane of the magnitude of the cross product of the two vectors as we discussed above, integrated with respect to the area in the UV plane. So here's a very brief explanation of where this double integral comes from. Let's go ahead and take a look at it formally. If we have a smooth surface given by r of uv, the surface area is given by this double integral here, which we just discussed. Now we should mention in the next video that if the surface is given as z equals g of xy over the region in the xy plane, there is a shortcut for determining the magnitude of this cross product, as we see here. But in this video, the surfaces will be defined as vector-valued functions. Let's take a look at our first example. We're going to determine the surface area of the cylinder given by the following vector-valued function, where u is on the closed interval from 0 to 2 pi, and v is on the closed interval from 0 to 4. So let's first find the partial derivatives of r. The partial derivative of r with respect to u is going to be negative 3 sine u, 3e cosine u. Then the derivative of v with respect to u would be 0. And then the partial derivative of r with respect to v is going to be 0, 0, and 1. So now we need to determine the cross product of these two vectors and then the magnitude of that result. I'm going to go ahead and use the diagonal method to determine the value of this 3 by 3 determinant. So I'm going to go ahead and copy the first and second column again. So we'll sum the product of these three diagonals, and then we'll subtract the product of these diagonals, 1, 2, and 3. So the result of the blue diagonals will be 3 cosine ui, and the result of subtracting the green diagonals will be, 3 sine u times j. Now we need to determine the magnitude of this vector to determine the integrand of our double integral. So let's do that on the next page. So we'd have 9 cosine squared u plus 9 sine squared u. When we factor out the 9, we're going to have cosine squared u plus sine squared u. That's going to be equal to 1. So we have the square root of 9, which is equal to 3. So to determine the surface area, we're going to have the double integral of 3 integrated with respect to u, and then with respect to v. And the intervals for u and v were given. So 3u well, this is just going to give us 6 pi. So we'll have 6 pi v and that's just going to give us 24 pi. So this would be the surface area of the cylinder defined by this vector valued function in two parameters given these intervals for u and v. Let's take a look at one more example. Let's take a look at a second example. Here we want to determine the surface area of the sphere given by the following vector valued function on these intervals for u and v. So again, we first have to determine the partial derivatives of r. So we first need to determine the partial derivatives of r. So the partial derivative of r with respect to u is going to be 2 cosine u cosine v, 2 cosine u sine v, and negative 2 sine u. Then the partial derivative of r with respect to v, well, this would give us a negative sine v, so we'll have negative 2 sine u sine v. The derivative of sine v would be cosine v, so we'll have 2 sine u cosine v, and then here we'd have 0. So now we need to determine the cross product of these two vectors and then determine the magnitude of the result. So to evaluate this cross product, again, I like to use a diagonal method. I've already set this up here. So we'll sum the product of these three diagonals. There's 1, there's 2, and there's 3. And then we'll subtract the products of the diagonals in the other direction. So we'll subtract the product of this diagonal, and this diagonal. And since we're running a little bit short on time, I've already determined what that would be. And now we need to determine the magnitude of this vector. So we'll take the square root of the square of each component. Now we're going to end up factoring this to simplify. Looking at these first two terms here, if we factor out the common factor of 16 sine to the fourth u, we'd have cosine squared v plus sine squared v, and that's going to give us 1. So these two terms simplify to 16 sine to the fourth u. Now if we take this and factor out 16 sine squared u, we're left with sine squared u here plus cosine squared u here, which gives us 1 again. So this finally simplifies to the square root of 16 sine squared u, which gives us 4 sine u. So this will be our integrand to determine our surface area. So we had to perform all of that work to determine the magnitude of this cross product, and again it came out to 4 sine u. And we'll have du dv. Let's go back and take a look at the intervals for u and v. They were from 0 to pi and from 0 to 2 pi. So u is from 0 to pi and v is from 0 to 2 pi. So now it becomes pretty straightforward. Here we're going to have negative 4 cosine u well, cosine pi is equal to negative 1, so we'll have 4 minus, and then when cosine is 0, we'll have 1, so it'll be negative 4. So we're going to have 8v. So we're going to have 16 pi for the surface area of that sphere. And that's going to have to do it for this video. Thank you for watching.